Okay, so let me remind you that if you want to ask questions during the talk, you can just unmute yourself or raise the hand, and then somebody is going to unmute you to ask the question. So, but if you, well, it will be better if you wait until the end of the talk, and there will be time to ask questions then. Okay, so let's start. So next speaker is Xingbin Pan from Chinese University of Hong Kong, and he's going to speak about the Maxwell-Stokes system. So please.
Thank you. First of all, I would like to thank organizers for invitation and for organizing this wonderful conference. The title of my talk is on Maxwell-Stokes system. My talk consists of 4 parts. In the first part, I would like to introduce some known facts about the Q of vector fields. And the second part, I will explain why we need Maxwell-Stokes system. I will discuss a little bit about the relation between electromagnetism and domain topology. And then I will introduce a magnetostatic model with topological parameters. And in the third part, I will talk about the representation of Q functional by using the modified Dirichlet lemma. And in the last part, I will discuss solvability of the magnetostatic model and a general Maxwell-Stokes system. My talk is based on the following 3 papers. The first one, 2016, calculus evaluation PDE, and second one, 2020, DCS, and the last one, this year, JDE. Okay, let me start with the known facts about Q. Given a vector field U with components U1, U2, U3, and you know that Q of U is the anti-symmetric part of grading U. That means that if you only control Q of U, you cannot control the grading, so you do not have any compactness. And many times we use the second order equation, second order operator QQU, or you write Q square U. And this operator is degenerate. In fact, that if you write it in the standard form and calculating the characteristic form, and you will see that the characteristic form vanishes everywhere. And then any question involving the QQ operator, because it is a degenerate elliptic equation. So the type of boundary condition has to be posed according to the geometry of the domain and according to the structure of the equation. And that increases a lot of complexity. We assume that the domain omega is a bounded domain with smooth boundary, and the boundary partial omega has m+1 connected components. In other words, it has m holes, or you can say m is the second Beatty number. And we also assume that the domain is multiply connected. So you color the domain with n 2-dimensional manifolds, and then the remaining part, omega dot, will be simply connected. And the number of cuts, n, is called the first Beatty number. And you can also say n is the number of handles of the domain omega. So associated with the domain topology, there are 2 spaces of finite dimension. The first is H1, which consists of vector fields with Q of U equals 0 and divergence of U equals 0 in omega, and the normal component equals 0 on the boundary. And any vector field in this space is called the Neumann field. Another space, H2, consists of the vector fields with Q equals 0, divergence equals 0, and tangential component U sub t equals 0. And H1 and H2 carry information of the domain topology. For example, dimension of H1 is n, the first bit number, and dimension of H2, little m, is the number of holes. So you can understand the domain topology through these two spaces. Okay, we use the notation H of omega Q0 to denote the kernel of Q, which is the set of all L2 vector fields U such that Q of U equals 0. And we also denote H of omega divergence 0, the set of all L2 vector fields U such that divergence equals 0. And these two sets could be complicated if the domain has complicated topology. For example, if a vector field U has Q0, and if omega is simply connected, then U is a grading field globally. But if omega is multiply connected, this is not the case. And actually, kernel of Q consists of two parts, the grading fields part and the space H1. And the kernel of divergence consists of two parts, Q of H1, the image of Q, and the space H2. So you can see that the topological domain enter the kernel of Q and enter the image of Q. And the kernel and the image actually related to the equations involving the operator Q or QQ. So we know that Q of H1, the image of H1 and Q consists of the space H gamma, which is not just the vector fields with divergence 0. Actually, it is more condition on that. So for a vector field belonging to the image of Q, of course, divergence must be 0, but it must also satisfy some additional condition. And the integral of normal component of U on each component of the boundary must be 0. And if we prescribe the boundary condition, say tangential component equals 0, then the image will be in the H sigma, which is the set of our vector fields with divergence 0, but also the integral of normal component on each cut, sigma I, must be 0. So let's consider equation of the following form. Q of some nonlinear vector field H of Q of U. H is the vector valued function, and the right side is f of U. It could be given depending only on x, or it could depend on U. And if this equation and some kind of boundary condition has a solution U, then the left side belongs to the image of Q, and the right side must also. And this means the right side must satisfy some actual condition. And if omega has no holes, then divergence of f equals 0 is enough. But if omega has holes, then f must belong to H gamma. And for the linear equation, it is not a problem. You assume the right side, the given vector field satisfies some condition, then you solve a problem. But for nonlinear equation, you try to use method of operators to solve this equation, and you wish that the right side give you an operator. But to use the method of operators, you wish that the right side maps the set into image of Q. However, there is no obvious way to guarantee this point. I also want to mention the Hodge decomposition. And for linear problem, Hodge decomposition is very useful. Given a vector field U, you can decompose it into two parts, divergence-free part and grading field part. The reason is, if you have an equation involving Q, then somehow you have control on the Q of U. But this is not enough to control the grading. Then, if you know that the divergence of U equals 0, then you have good estimates. But if you does not satisfy the divergence-free condition, and if you can decompose it into two parts, and for this V, you know that the divergence is 0, and you have good control. Then you can separate your equation into two parts. One is for phi, one is for V, and for the part for V, you have good control on the curl and the divergence, and you solve problem. So for linear problems, you don't see much difficulty in this part, and you can use Hodge decomposition. But for nonlinear equations, Hodge decomposition does not help much, and this gives us a lot of trouble. Okay, now we go to the part 2, why we need a Maxwell-Stokes system. Let me start with the classical form of Maxwell equations. And here, E denotes the electric field, B is the magnetic induction, H is the magnetic potential, and J is the electric current density. And this is the classical form we use a lot. So you look at these equations, and you get the impression that the magnetic fields and the electric fields actually are most fundamental to understand the electromagnetism.
Excuse me, it should be curl B, right?
Curl E and curl H, curl H actually. And for linear equations, usually people use the relation H equals mu B, and you reduce to the equation for B. But H could be, has a nonlinear relation with B. So this should be, am I right?
Okay.
Okay. All right, now, because for the second equation, divergence of B equals 0, and if we assume that this condition holds in the whole space, then the whole space is simply connected, and you can introduce magnetic potential U and write V equals Q of U, and plugging this relation into the Maxwell equation, and you can eliminate the B, and you have equations for U and for E. And then it is a question that, can we understand the electromagnetism only use E and B, E and U, or E and H? So actually, you look at the original equations written by Maxwell himself. He used unknowns involving the magnetic potential. And then Heaviside introduced the vector form without the magnetic potential. So people think that probably the magnetic fields are most fundamental. However, in 1959, Aronoff and Bohr, they published a paper, and they predicted that electrons may be influenced in the form of phase shift by electromagnetic fields, which the electrons do not experience. And now we understand that Aronoff-Bohr effect is due to the fact that the domain is non-trivial. The domain topology is non-trivial. So it suggests that to answer the original question, which one are most fundamental, magnetic field or magnetic potential? The answer really depends on the domain topology. And this suggests and motivated our study for the following two problems. The first one is to study partial differential equations of magnetic potential U, maybe coupled with E, and examine the effects of domain topology on the solvability. And the second one is to study a general magnetostatic model with domain topology as the parameters. And understand this special case may help us to understand the domain effect on the original Maxwell equations. And here I want to mention that the effect of domain topology on equations have been studied by many people. For example, Barré and Cohon in 1988 studied the domain topology effect on the elliptic equations involving critical Sobolev exponent. And in 1999, Beijing-Rubinstein studied the domain topology effect on the Ginzburg-Lambda equation, and Bernard and his collaborators studied the domain topology effect on the spectrum of magnetic shielding operator. And last year, jointly with Neumann, we studied the domain topology effect on surface superconductivity. Okay, now I want to explain why we move from Maxwell to Maxwell-Stokes. Let's consider the equation Q of H equals F. And this equation comes from the Maxwell system, but we drop the term partial T E, and this is so-called quasi-static approximation. And after you drop this term, and then you get the equation Q of H equals F. But this F could be giving vector field and could depend on magnetic potential. And for nonlinear material, the relation between magnetic field H and magnetic induction B is nonlinear. We have nonlinear relation, and you plug in B equals Q of U, then you get the second order equation, Q of H of Q of U equals F. Right? And F could depend on U. Now, you can consider the following problem. Besides this equation, you also assume that the divergence of U equals 0 in the domain, and you give the Dirichlet boundary condition, assign the tangential component of U. Okay? And this equation is solvable if and only if the right side F belongs to the image of Q. Of course, and some reasonable condition on the nonlinear vector field, vector valued function H. And if H has no holes, then you only need to assume that F has divergence 0. But if omega has holes, F must belong to H gamma, which is the extra condition. So one point of view is if the given F cannot satisfy this condition, so this given equation may not have a solution. What we can do is we try to make some relaxation. We replace F by F plus grading field. And you require this grading field to be chosen such that F plus grading phi belongs to the image of Q. In other words, if omega has holes, then you make F plus grading phi satisfy that extra condition on the boundary. And then you move from Maxwell to Maxwell-Stokes. You can have such kind of equation. And with this extra term, you have more freedom to have a solution. Okay. So we borrow the name Stokes from Navier-Stokes and use this just for convenience. And after you introduce this term, you also needed to worry about the boundary condition of this phi. And for equations involving Q of U, the type of boundary condition for this phi must be prescribed according to the domain topology. And this is not the same as the Navier-Stokes equation. For example, if the domain has no holes, then it's okay if you assign the Dirichlet boundary condition, let phi equals 0. And we will show later that due to the modified de Lamre lemma, we are able to solve this kind of problem. But if the domain has holes, the Dirichlet boundary condition for phi is not good. Instead, we need to have Neumann condition for phi. And the right side minus CFU is piecewise constant function. It defined in this way. Gamma I is the connected component of boundary partial omega. Then on each component, you have integral of the normal component of F and divided by the area of this piece of connected component. And this gives you a constant. So C of FU is piecewise constant function, but it depends on U. So for domain with holes, Dirichlet boundary condition for U for phi is not good. Neumann condition is fine. Okay, now you see that we introduce the term grading phi into the equation to balance the equation. Mathematically, it makes the equation solvable. But do we have any physical explanation of this term? The reason why we need this term. So let us look at the magnetostatic model, which is derived from the classical Maxwell equation. We assume also that the current density J satisfies Ohm's law. It means that the current density J not only depends on the given current density, but also depends on the electric field E. And sigma is a non-negative constant of scalar function, which is called the electric conductivity. So J equals JA plus sigma E. Then maybe I skip these computations. So we start from the second line in the Maxwell equation, divergence of B equals 0 in omega. So B is in the kernel of divergence, then it can be written as Q of something plus H2. H2 is in the space H2, it is the Dirichlet field. Okay. Then plugging back to the first equation, partial TB plus Q of E equals 0, and plugging B equals Q of H plus H, Q of W plus H2. And then we find that Q of this one plus partial T H2 equals 0. Then each term must be 0. And then E plus partial dW must lie in the kernel of Q. Then you can write down that it is grading field plus H1, the Neumann field. Okay, then you introduce A equals W plus grading theta. Theta is the integral of Cassi. You can derive this equation, okay? And then you make a little bit more simplification, and finally you have the time-dependent equations. This U is the magnetic potential. So sigma partial T_U plus Q of H of Q of U plus H2 equal GA plus sigma H1 plus sigma grading Q. And here, U is the magnetic potential, H1 is the Neumann field, H2 is the Dirichlet field. Okay. And you have extra grading field. Okay. And if everything is independent of time, then you have a simpler equation, Q of H of Q of U plus H2 plus G equal GA plus H1 plus grading phi. So you do see the grading field in the right side. And this grading field actually is related to electric field. Electric field E is given by grading phi and H1. So you can say that the grading field represents the electric field and also carry some information about the domain topology. Okay. So this equation carries H1 and H2, and we say this is kind of topological parameters. You solve U for some parameter H1 and H2. Okay. So now see that although mathematically this grading phi is introduced to balance the equation, but physically, in some situation, it does have physical meaning. It represents the electric field E and represents the domain topology through the Neumann field. Okay, now we move to third part, the representation of Q function. We start with the modified Dirac lemma. And you know that the Dirac lemma says that a bounded linear function vanishing on H01 divergence 0, the Sobolev space with 0 boundary data and with divergence 0 inside the omega. Okay, if you have a functional vanishing in this space, then this functional can be represented by gradient phi. And you know phi belongs to, say, L2. And the Dirac lemma does not give you the information of the trace of phi on the boundary. And for our purpose, somehow we need some information. Okay? And we consider the following two spaces. One is W1P T0. T0 means that every element in this space has tangential component 0. And inside domain, divergence 0. And W1P N0 means every vector field in this space has 0 normal component on the boundary. And we consider the functionals vanish this one of these spaces, and we wish to derive the representation. Okay, so we assume that omega is a bounded domain again in space, and P is bigger than 1, a positive number, and we use P prime to denote the conjugated index, and P star to denote the Sobolev exponent for the embedding W1P into LP star. And we also need P star prime and P prime star. Okay, for space X, a bounded space X, we use the X star to denote the dual space. And if we have some space LP omega, then we use dot. Dot LP means the subspace of LP consists of the functions with integral vanish C. Okay, now giving any function, scalar function phi in L dot P prime and any theta in the trace space, we can define a functional T sub phi theta on the space W1P T0. Again, T0 means every W in this space has a tangential component 0. Then we define the functional to be minus phi divergence W and integral in the omega and theta times normal component of W and integrating on the boundary. You can think that this is actually the grading of something, grading of phi, but we do not have grading for this kind of phi. And actually, this is a well-defined functional, and the set of all such kind of functionals give you a space homeomorphic to the original LP prime times the trace space. And you can also define when theta equals 0, T phi, you drop the boundary term. Right. Okay, then we have the following conclusion. Assume you have a functional, a bounded linear functional acting on W1P T0. Acting on W1P T0 and vanish on the subspace with divergence 0. Right? So for any W in W1P T0 and divergence equals 0 on the bound in the omega, then this function equals 0. Then we have a function phi and constant C such that this functional can be represented by T phi C. And remember, phi means you have integral involving the divergent W, and C appear in the boundary integral. Okay, now we go to W1P N0, the normal component equals 0. Okay, so again, you have for any function phi and for any Z in this kind of trace space, you can define the functional T phi Z in this way. phi divergence W integral omega, and W dot the tangential component of W on the boundary. And again, you have the space, and this space of the functionals is homeomorphic to LP close this trace space. And if Z equals 0, you can define T phi 0. Okay. And similarly, we have the following conclusion. Suppose you have a functional T on the W1P and 0. And suppose this functional vanishes in the subspace W1P and 0, divergence 0. Then this T can also be represented by T phi. Okay, so far you still do not see the information of the trace, but now we can get more information for more concrete situation. Suppose that you have vector field U and G and capital U, such that A is a matrix or matrix valued function. AQ of U belongs to LP prime, and G belongs to LP prime, and capital U belongs to LR. R is bigger than or equal to P star prime. Okay. And for this capital U, you can define function phi ud, which is the weak solution of the Dirichlet problem. Laplacian equals divergence of U in the weak sense. And you can also define phi un, which is a weak solution of the Neumann problem. Okay, so this phi du is in the W1R space, and phi nu is also in the solid space. Okay, now we have the following lemma. And the condition we given before assume that we have some kind of equation. So this equality holds for any W, for any test fields W in the W1PT0 with divergence 0. So W has tangential component 0. And we have this kind of weak solution. Okay. And then our conclusion is actually you can find some function phi du, which we defined before. And this functional can be represented by the grading of phi du. And because phi du belongs to the solid space, it has a trace and a trace 0 on the boundary. So we can represent the functional by using the grading field, and we have information of this phi about the trace of phi. Okay. Next, if we consider the space W1P and 0, then U and G and capital U satisfy the condition before, but we also have some boundary term. So you assume that you have some WT, which is tangential vector field, and belong to some trace space. And this tangential vector field can act on W on the boundary. So we have an equation in the weak form. And W. In other words, this functional can be represented by grading phi. And we know more about this phi. Actually, this phi can be written as n phi nu, which we defined before, the weak solution of the Neumann problem, plus psi. And psi has Laplacian equals 0 in the weak sense. So these two functions, phi nu and psi, both have trace on the boundary. So we can have a little bit more information on the representation phi. We know that it has trace on the boundary. And with above these two lemmas, we can use them to study the equation of the following form. and we can discuss existence and multiplicity of solutions. Okay, now we go to the fourth part, solvability of the magnetostatic model, and then solvability of Maxwell-Stokes system. And you already saw this equation. We derive it from the Maxwell equation and the additional condition that the electric current density satisfies the Ohm rule. Okay, so now U is the magnetic potential is unknown. And H1 and H2, H1 is a Neumann field, H2 is Dirichlet field. We treat them as parameters. And you can treat phi as unknown. But if J is giving vector field, if it is independent of U, then actually we can solve this phi. Okay. So here we list some conditions on H to make this equation go to elliptic. Okay. So if the right side of J is given, and if it is independent of U, and if it is orthogonal to H2, and remember H2 is the set of all Dirichlet fields, then we can write J as this J belongs to the image of Q plus gradient theta. Okay. And then plugging this back to the equation, actually you can solve phi. So in this special case, when J is independent of U, you can determine phi, and you can reduce everything to only one equation for U only. And then we have this kind of equation, and we call it Maxwell system or Maxwell type equation. And you can pose either Dirichlet boundary condition or Neumann boundary condition on U. Here we first consider Dirichlet boundary condition. So tangential component of U equals a given vector field U0T. U0T is given. And also you assume divergence of U equals 0 inside the domain. And then we can show that this system has a weak solution, and it is H1, quite good. And if you put some orthogonality condition, you can have uniqueness. The orthogonality means that if the boundary data has attention into the domain omega, and you choose carefully the attention U, such that U minus capital U is orthogonal to all the Dirichlet fields, then this solution is unique. Okay, to prove, because the right side J plus H1 belongs to H gamma, the image of Q, so you can write down J plus H1 as Q of another J, J0. And then plugging back to the equation, you see that everything is in and the Q. So you can write down that you can use the inverse of H to write the equation in this form. And this changes to the first order equation. To make this equation solvable, actually you need the right side belongs to the image of Q. And first, it must be divergence free. And second, it must be orthogonal to the H2 or H1, depends on your choice. Okay. And here, phi is unknown, so you try to find some phi to make this right side belong to image of Q. So we say that for the given J0 and H1 prime, this system is solvable if and only if the following conormal problem for phi has a solution and phi satisfies the orthogonality condition. This right side is also orthogonal to H1. And then it guarantees that this term is in the image of Q. Then you can solve this equation because the right side is in the image of Q, you find some V. And after you find some V, you go back to U. and you will give you the original solution of the original equation. Okay. To get this result, actually we represent the H1, the final dimensional space. We found an orthonormal basis. And then you represent every Neumann field as a combination of this base. And then for each Cassie, you find H1 prime, plug into equation, you find phi. And you can use, use the monotone operator method to solve phi. And after you solve phi, you need to choose this phi such that the orthogonality condition is satisfied. And actually, we reduce everything to a map in final dimension. So this one comes from the orthogonality condition. So you assume that you choose base in this H1 and you run this equation. Actually, you run ETS n equations. You choose H from the base. Okay. Then you define the F and CI. So you solve equation of finite unknowns, and it can be written as a map in finite dimensional space. And then you can show that actually, you can find some large R. If Cassie is on this sphere, then you have F Cassie minus the C, you giving C is make an accurate angle. And then you use the accurate angle theorem for a continuous map in finite dimension. If you have this condition, it has a solution inside of the ball. And this solution, Cassie 0, give you the H1 vector field and produce the phi Cassie, which satisfies the equation as well as the orthogonality condition. And then it gives you the solution V. Okay. Next, we can also consider the problem with natural boundary condition, kind of Neumann. And use similar argument, you can also have a solution. And the solution, if you give more actual condition that the solution has 0 normal component also going to H1, solution is unique. Okay. And this can be done by using monotone operator method. Okay, finally, I want to talk about the solvability of Maxwell-Stokes system. And we consider omega as a whole, in the case omega does not have a whole. So if omega has no holes, as I mentioned before, you can give the boundary condition Dirichlet type for this phi. And then, okay, some reasonable condition on F. Okay. So you consider some extension of boundary data, and you subtract this extension, and you have new vector field V, and V satisfies the homogeneous boundary condition. And you write the right side as a projection, and this is actually the Rayleigh projection because you choose phi such that F plus gradient phi has divergence equal 0, and the phi has 0 boundary data. So it is actually the Rayleigh projection. And then you can write an equation in this form, and then use the operator method to show that this equation has a solution. And actually, if the H and F is smooth, you can show that the solution is actually quite good. U is C2 plus alpha, and phi is C1 plus alpha. Phi has 1 order less regularity than U. Okay, now if omega has holes, then we have to consider Neumann boundary condition. Again, you give one U, you let the right side, you let phi Okay, so if this equation holds, then the left side is divergence free. The right side is also divergence free. And it gives you the equation for phi. And then we must have this type of boundary condition for phi. So actually phi is determined by U. And it gives you some kind of projection of on the right side. So Fu plus gradient phi, for phi decided as we mentioned, it is a projection of F. And then use the operator method again, you can have a solution. So more or less similarly, you can show the existence of solution. And again, you can show U is C2 plus alpha and phi is C1 plus alpha. Okay, now we are still working on the case, working on the problem, how to get the more information about the topological effect from H1 and H2, and to the elliptic equations and to the time-dependent problems. And this is still quite interesting and not finished yet. Okay, thank you very much for your attention.
Thanks a lot, Me. Thanks a lot for your talk. So is there any question?
Oh, probably I have.
Yes, Iman, you can go.
Okay. So thanks, Xingbin. So the question is about, I have an idea that your equation discussed in the context of electromagnetism, but also in other contexts like superconductivity. So you have this kind of curl squared A equal to the current. So usually we escape from exploring the phi you introduce by introducing variational spaces. So do these potentials phi that you introduce may account to singularity in that context? For example, have you any comments on that?
Okay, so you're right. If you have complicated domain, this phi could have singularity, yes. And I believe that if we look at the time-dependent problem, it could have more singular situation. For elliptic case, probably if we assume F is smooth and H is smooth, then more or less you can control phi. But if F is not so smooth, of course, phi could be very bad. And for the time-dependent problem, I guess that we have more chance to have singularity for this phi. And if you look back to the Ginzburg time-dependent Ginzburg-Lambda equation, and they have another phi which appear in the left side, and not exactly as a phi we have right now. They have another one, and for another one, because the gauge invariance or something, you have more choice of that phi, and it have more chance to introduce singularity. And for phi in my equation, probably it has better regularity. Do I answer your question?
Yes.
Yes, thank you very much.
Okay.
Thanks, Xingbin. So Douglas wanted to ask another question, I think. So you can
hello, thank you. I was thinking, since you have this all this topology in the problem, do you also, or have you thought about considering some kind of Chern-Simons term into this framework, or whether there is some topological connection there?
So what is Chern-Simons?
Sort of look at the I guess it's sort of a way to incorporate some topological effects into the problem. I don't know, with the connections having some non-trivial topology. I don't know. Maybe it's a it's a different story to think about.
Okay, I'm sorry for my
no
ignorance. Probably I will research the Simon stuff.
Thank you.
Okay.
More questions? Etienne wanted to ask a question, so I think you can.
Oh yeah, so the gradient of phi would be like a pressure term in Euler equations or something like that.
Yeah, it's very similar to the pressure. Yes, very similar. And you see, if we compare my equation with the Stokes equation, the classical Stokes equation, and you have minus Laplacian u plus something equals gradient phi. And if you put the divergence-free condition for u, then minus Laplacian u could be written as QQu, and this is exactly the same. But for the Stokes equations, usually you have different consideration. You have different kind of boundary conditions. And here, usually, the boundary conditions could be different. For example, if you look at the Stokes equations, you may assume that u satisfies the whole Dirichlet boundary condition, prescribe the whole trace, tangential and normal component. Then you do not need to prescribe the boundary condition for phi. And in my case, you cannot prescribe the whole trace of the u. You can only prescribe either tangential part and the normal part. Then some boundary condition for phi is necessary. Otherwise, you have too many solutions. Okay, for linear problems, it's really very similar to the Stokes equations. And the gradient term is actually the counterpart of the pressure term in the Stokes. And for the nonlinear case, actually quite a different situation will occur here.
Okay, thank you.
Okay, any more questions? Seems to be the case. At least I don't see any hand raised. So I think we can stop this morning session and this point and resume then at 3 p.m. Beirut time, so 2 p.m. European time, or Douglas talk in the afternoon. Maybe Uvafa, you want to add something, or Ayman, do you want to add something about the organization, or?